Hi all, I'm Navneet. I have with me Aseem and Aditya here, and we'll cover solidification of alloys week 9. We'll cover here four topics. First is solute partitioning, second is constitutional supercooling, third is cell structure and morphology, and last is cellular and dendritic growth. Okay, we start with solute partitioning. Here we take a assumption that in solidification of metal, there is equilibrium at the interface and there is no barrier to transport of atoms. We consider a single crystal of alloy C0 and the equilibrium will be attained at temperature below TL. If solidification occurs at temperature T star, then concentration of a solid will be CS star and liquid will be CL star. Under these conditions, we define a partition coefficient that is CS star upon CL star, and it is constant because of straight line of liquidus and solidus. Okay, now we come to the case no diffusion in solid and perfect mixing in liquid. Here we consider a crucible of length L with initial composition C0. The initial solid that will form will be at TL of composition KC0. During further cooling, liquid become richer in solute, and because of no diffusion, composition of solid in initial stages is same. At T star, solid CS star composition is freezing from liquid composition CL star. Expression is given here by equating solute rejected when a small amount of solid forms with resulting in increase in liquid, which after integration becomes CS star equal to KC0 into 1 minus Fs to the power K minus 1. It is also called Scheele equation. From here Aseem will continue.
Next case deals with solidification of single-phase alloys subjected to the condition of diffusional mixing in liquid. Here, solidification begins exactly as in previous examples with the initial solid forming of the composition KC0. The solute rejected into the liquid is transported only by diffusion, and so an enriched solute boundary layer forms and gradually increases in solute. The three regions shown in the graph alongside are initial transient, steady state and final transient. Solute composition in liquid in steady state region is given by the following equation: Cl equal to C0 1 plus 1 minus K upon K e to the power minus R by dl x prime. dl by R is called a characteristic length, that is the distance at which the quantity Cl minus C0 falls to 1 by E times of the maximum value C0 into 1 by K minus 1. Zone refining is a practical application of above mentioned case. It uses the fact that material solidifies with higher purity than surrounding liquid. Concentration of solid formed is given by the following equation: Cs star upon C0 equal to 1 minus K e to the power minus Kx upon L. It produces metals of purity up to 99.99%. Now we will consider effect of convection. A new partition coefficient K prime equal to Cs upon C0 is defined here, and solute concentration is given by following equation: Cl star minus Cs star upon C0 minus Cs star equal to e to the power R delta upon dl. Delta is the boundary layer thickness, that is, concentration in liquid becomes C0 after moving delta distance in liquid from interface. The relationship K prime equal to K upon K plus 1 minus K e to the power minus R delta by dl is of considerable engineering usefulness because it relates the composition of the solid forming in the crystal growth to alloy composition and growth condition. The solute concentration is given by the following equation: Cs star equal to K prime C0 1 minus Fs to the power K prime minus 1.
Constitutional supercooling, as the name suggests here, supercooling arises due to change in composition. Graphical representation of supercooling criteria is given alongside, where if actual temperature is greater than liquidus temperature, then a small perturbation which arises melts away and plane front solidification occurs. At steady state with no convection, constitutional supercooling criteria is given by the following: GL upon R greater than equal to minus ml C0 1 minus K upon K dl.
If constitutional supercooling occurs, then planar interface becomes unstable and they become gently undulatory. Protrusion develops followed by formation of fully grown cells and hence completely solidified alloy. Now Adit will continue further.
Till now, whatever we saw was a planar growth and a little bit of cellular growth. Planar growth, as we saw, occurs for high GL by R values. And now we will see how cellular and dendritic growth occur. Now, as growth conditions depart from those required for plane front, a number of transition structures are observed. The structures obtained depend also on crystallographic orientation. In the crystals growing in a 110 direction, elongated cells develop with the segregated concentrated in the planar intercellular regions. In the crystal growing in a 100 direction, the segregate is concentrated in roughly cylindrical regions termed nodes. The liquid-solid interface for the two orientations discussed above is shaped as shown schematically in the diagram on the left. Furrows develop on the interface in the case of the elongated cells, and regularly spaced depressions develop in the case of the nodes. A probable, although superficial, explanation of this effect of crystallography on interface morphology can be explained like this. In the case of 100 growth direction in cubic metals, a perturbation on the interface will have four symmetrically placed regions of 111 orientation. This is the closest packed plane and is expected to be the slowest growing. Thus, these four slow growing regions guide the shape of the perturbation to be of roughly equal dimensions traversed to the heat flow direction. The relatively small amount of segregate in the dilute alloys with high GL by R then concentrates in the lowest positions of the interface as nodes. In the diagram, we can see the same thing. The direction 100, the growth direction when it's 100, you can see the nodes being growing in all the directions. In case of the 100 oriented crystal, on the other hand, a perturbation will have on it two but not four such slow growing planes, guiding the interface morphology to a furrowed structure and leading to elongated cells. In the diagram, as you can see, the 110 direction being shown, that is one of the directions in which the growth will take place. The other direction in which the growth takes place is into the paper, as you can see. Now we will see how a dendrite is formed. When regular cells, such as those shown before, form and grow at relatively low rates, they grow perpendicular to the liquid-solid interface, regardless of crystal orientation. Although, however, as explained before, growth rate is increased, crystallographic effects begin to exert an influence and the cell growth direction deviates towards the preferred crystallographic growth direction. For example, as I explained before, 100 for cubic metals. Simultaneously, the cross-section of the cell generally begins to deviate from its previously circular geometry owing to effects of crystallography. This structure has been described variously as a flank structure or a Maltese cross in cubic materials. A Maltese cross can be seen a little bit in the diagram B and C and D, all the three of these, but the intensity of the Maltese cross increases as we go from B to C to D. As growth rate increases still further, the cross structure first becomes more apparent and then serrations begin to appear in the flanges of the cross. That is, secondary dendrite arms become discernible. What we can see in the diagram D is that secondary dendrites are coming out. Those serrations can be seen very, very clearly. Overall, about dendrites, what we can say is that when secondary arms appear in cells, the structure is usually termed dendritic. We use the terminology like this. When initially a cell grows, it's just called cellular growth, but when secondary dendrites appear on it, we call it dendritic growth. The dendritic growth depends on intercellular composition. Lateral growth of tip results in partitioning also led to favorable condition for secondary and tertiary arms. If ejected solute is not able to diffuse and primary dendrites grow close by, then there is a uniform distribution of solute perpendicular to the primary dendrites. This leads to cellular structure with no secondary dendrites. So dendritic growth also depends on amount of supercooling and also the growth rate. Now, here we can see the dendritic growth. Initially, the first diagram will show you cellular growth in our terminology. When growth rate increases and enough supercooling is provided, the primary cell growth is followed by secondary and tertiary dendrites, as can be seen in the diagrams B and C, or rather the second and third diagrams here, which eventually combine to give a fully solidified state with little imperfections called pores. Now, we'll explain the difference between cellular and dendritic growth. For a planar growth, as we saw, the temperature of the melt has to be greater than liquidus temperature at all the times, so that when a perturbation comes on the liquid-solid interface, it melts back and we get planar growth like all the times. But for a dendritic growth or a cellular growth, the necessary condition is obviously constitutional supercooling, as we saw earlier. According to the graphs on the left, we can see that for lesser supercooling we have cellular growth, and for greater supercooling we have dendritic growth. Thank you, that's all for this presentation.